Okay, welcome to another video. In this last video, we show you how to solve problems 8a and 8b. So for problem 8a, notice that we're given a very comparable description to the clique problem. In fact, the only difference is that we have a bound on the degree here, so dv, right? And we're already given in class that we have an algorithm for this clique problem, which is brute force. It is in big O, n to the k squared. Okay, so the idea is that we can adapt this same algorithm, which is brute force, to our work here, but this time we're going to have to bound k. And once we bound it by a number, then this becomes a polynomial time in n. Okay, because currently it's exponential in k, but once k is bounded, then this becomes a polynomial time, and we can basically prove that there is a polynomial time algorithm for this problem, so it is in P. Okay, so how does this work? Well, we note that if k is greater than 4, then return false. Why is that? Basically, if you have a clique, okay, so something like this, notice that I cannot, because the integree or the degree is bounded by 3. Right now this has degree 3, degree 3, degree 3, and degree 3. Now, I cannot have a clique of size 4 here, because if I did, then I cannot have a clique of size greater than 4, because if I do, then the degree has to be greater than 3. Okay, but we know that it's bounded by 3, so then we cannot have k greater than 4. We can have k equal 4, right, because that would be just the maximal clique here, but we cannot have any k greater than 4. Okay, so if k is greater than 4, then return false. So then what's left is we search all subgraphs. Okay, now search all subgraphs of size k, or basically of k vertices, in G, and examine big O k squared edges to determine whether the subgraph is a clique. Okay, now notice that since k is greater than 4, then when k is greater than 4, then the time complexity becomes constant. We just return false. Okay, oh, by the way, let's just continue this. If there is a clique, return true, else return false. So basically this is our algorithm, and it is polynomial indeed. How? Well, since when k is greater than 4, then the time complexity is constant, and we only worry about when k is less than or equal to 3. But when k is less than or equal to 3, then the running time is what? Big N, or in this case, it's fine, I'll lay it as N, big N k squared, which is big O n cubed, and well, this is 3 squared, which is big O n cubed, where n is the number. Well, you can just say where n is equal to this. Okay, we can do this because when k is greater than or equal to 3, the work is not constant as opposed to when I think, yeah, it's better to say 4. So I guess we could actually even, yeah, we could do, instead of 3 we should do 4. Yeah, because, you know, we're allowed, when k is less than or equal to 4, we're allowed to do work, which is basically, we gotta do this. But when k is greater than 4, then we cannot, right? So this is 4 squared, so this is into the 4, okay? Now we can do this because when k, the work is not constant, as opposed to when k is greater than 4, okay? So yeah, now this completes this problem. Now this one says, show that this problem is NP, yet we have shown that by given a polynomial time algorithm. Does this contradict the fact that the clique problem is NP complete? And the answer is no, it does not contradict that CP, or, you know, the clique problem is NP complete, because this is a specific, easier version of the clique problem. Okay, so this completes 8a, and now we do 8b. The composite numbers problem is defined as follows. Given the positive integer k, determine if there are integers m and greater than 1, such that their product is k. There is a root k time algorithm solving this problem. Is this problem in P and Y? So this problem is quite familiar to me. I've seen it many times, and if you haven't, I guess you can still like understand why this wouldn't be, because you'd have to search the integers from 1 up to root k. And so notice that we're actually, remember that when a time complexity is defined, it's defined in terms of the number of bits used to encode the input, okay? So if we add an extra bit, then we're going to double the search space, okay? What do I mean by this? So let's see. Let's think about if we have 3 bits. Okay, if we have 3 bits, then the search space goes from 000 up to 111. Okay, this is in base 10 would be 0. This should be, I believe, 7. Right? Yeah. Now, how many numbers we have searched here? We're searching 8 numbers, okay? Now let's increase the number of bits to 4 bits. What happens here? Then we get something like this. Okay, so from 0 up until 15. So now how many, so this is 8 is the size of the search space. This is how much or how many things that we search. And now here it's 8 times 2, which is 16, is the size of the search space. So basically, as we increase the number of bits, of the input by 1 bit, we double the amount of work. Okay? So then this big O root k is a pseudo-polynomial. It's just it's not like telling you that in the number of bits. It's telling you that in just the number, it's just in the integer itself. But this is not how we measure time complexity. We measure it in the number of bits, okay? So the actual time complexity then or we can say that, first of all, that big O root k is a pseudo-polynomial running time. The actual time complexity is exponential in the number of bits used to encode the input, i.e. big O 2 to the log of root k, which is half root, well, half log k. Now I understand that you were tempted to just cancel these out, but that's just not how it works with big O, and with the fact that this is just exponential, like, because it takes log 2 bits k to actually represent the input, right? But the actual work is exponential in that number of bits. It just happened to be a log function here. Maybe in a different encoding we don't use the log, we use a different function. But yeah, the point is that this is definitely exponential, and the argument is here. You can see that. Okay, so that's it. So what was the n? I believe that's just how we explain it. Yeah, so this problem in P, we said no, and why? We give our explanation here. Okay, hope this was helpful, and good luck on your exams.